We're going to be discussing blood pressure regulation during dynamic exercise. Basically, this whole block we've been talking about the changes in VO2 during exercise and the changes in blood flow. So today we're going to talk about how is blood pressure regulated with all these changes going on in the body during dynamic exercise. So we'll break this up into two videos. Today I'm going to discuss the first two learning objectives that you see on the slide here. The first one is to provide the answer to the question, is the baroreflex operative during dynamic exercise? And if it is operative, does it regulate mean arterial pressure during exercise? And so the reason why this is even a question is because what you guys know about the baroreflex is that we like to defend an operating point or a set point of blood pressure within our bodies. And then as that pressure deviates, if it gets higher, well then the baroreflex is going to ramp up parasympathetic nervous activity, turn down or downregulate the sympathetic nervous activity in order to bring blood pressure back to where it needs to be. If the opposite happens, if blood pressure drops too low, then the autonomic response will be flipped. We'll increase sympathetic nervous activity in order to bring blood pressure back to its operating or set point, right? And so during exercise, blood pressure increases. And so the question is, well, is then the baroreflex just turned off? Does it have a role in regulating blood pressure, allowing our blood pressure to increase, or is there some sort of other mechanism that allows the baroreflex to control our mean arterial pressure during dynamic physical activity, right? And then we're also going to discuss today the baroreflex resetting, so that's basically the answer to that first question, and the control of mean arterial pressure during dynamic exercise. And then we'll save a second video for the importance of actual vasoconstriction to the active skeletal muscle for blood pressure during maximal physical activity. And again, we'll save this for another video. I won't, go deeply into detail, but just as in everything with exercise intensity, we do reach a threshold or a limit. So the body has to decide at a certain point, are we going to keep on vasodilating to this active skeletal muscle to deliver blood, therefore to deliver oxygen? A consequence of that is going to be a decreased TPR. So do we try to regulate the oxygen delivery, or do we regulate mean arterial pressure? And more on that in the next video. But first, we should review our baroreflex curve, which you see here. So, this is our baroreflex curve. As you could see, our bodies operate, in this operating range here. Our minimum point of our reflex response is called our threshold, and then our maximum point of our reflex response is called the saturation. And so within this is where our baroreflex does operate. Here towards the flat portion of the curve, this is where the baroreflex is not really that effective at regulating blood pressure. So there is a minimum response past this minimum point and past this maximum point where the baroreflex cannot really help to regulate blood pressure if we get beyond these points, right? And so where we normally hang out and rest, right, our operating point or our set point is located very close to what is called our center point, which is the actual center of this curve, right? And this center point is what we call the max gain. And so just a reminder that this max gain or sensitivity of the baroreflex is typically 0.6 to 0.7, which translates to 60-70%, meaning that if the blood pressure is about 60 to 70% off its normal range, the baroreflex will be able to adjust. And so, researchers had a question because during the onset of exercise, there's what's called the exercise pressor reflex, where there is an increase in blood pressure. And so a pressor reflex is anything that brings up blood pressure, right? So, in the 1900s, even, before, there was a consensus that arterial baroreflex was turned off, right? That it didn't have a role during physical activity, because we saw that once people started exercising, their blood pressure increased. So, the thinking that the baroreflex should when intact, sort of oppose this, believed researchers to believe that the baroreflex was just turned on, right? And if it was turned on, that blood pressure shouldn't increase during exercise, right? And so this debate was, going on until the early 1990s, right? So not that long ago. And so there was, however, a lot of evidence saying that no, the baroreflex is not just turned off, right? It still has a role of regulating blood pressure during physical activity. So the primary question was, what causes sympathetic nervous activity to increase during exercise, right? So why is blood pressure increasing during exercise? And then how is that blood pressure regulated, basically, during dynamic exercise? So to that, we'll bring up these graphs here. And so, sorry about that, a lot going on here. So we'll just notice first that you have two separate graphs. This one says exercise 0%, and then this one says exercise at 21%. And what we're observing is changes in mean arterial pressure during low intensity exercise. So that's going to be this graph to the left here. And then during high intensity exercise, looking at this graph to the right. So we're looking again at changes in mean arterial pressure, the response. And so what happens when the baroreflex is intact? And so once we go from resting to starting exercise, our blood pressure is going to increase. We're going to see that increase in sympathetic nervous activity from the intact baroreflex. And then we're going to reach a limit of steady state, and that steady state is going to continue. That blood pressure is going to be maintained throughout the exercise, right? And so when that physical activity or that exercise is more intense, we see that increase in blood pressure to a greater degree, but again, it's going to reach that steady state, that limit, and then be maintained proportionally for that given exercise intensity, right? So when the baroreflex is intact, it helps to increase blood pressure, which is actually the opposite of, what researchers thought, right? So it's not turned off. It's actually serving to increase blood pressure during exercise. And so that's when both are intact. You see here that there's a pretty similar response when it's just one of either the aortic baroreceptor or the carotid sinus, that group of baroreceptors. When those are intact, they have a similar response. Again, you're going to see this increase in blood pressure, and it's going to be maintained throughout that physical activity. But what happens when the baroreflex is turned off during physical activity? So here, for the light intensity exercise, we see that as we go from rest to then actually exercising, because the baroreflex is not intact, we see a drop in blood pressure. Right? So the heart's going to pump out more blood to those muscles. We're going to get, vasodilation to those muscles. But then without that sympathetic nervous activity, without that baroreflex to signal for that increase in sympathetic nervous activity, we're going to see a drop in blood pressure. It's not going to be able to go up during exercise without that baroreflex, right? So again, the baroreflex, it's required for the increase in blood pressure. But then you look at this graph here to the right during that high intensity activity and you're saying, well, this is still going up. We're still seeing a mean arterial pressure increasing even though there's no baroreflex intact. So what is going on here? And actually, what you're seeing is an insight of the regulation of pressure during exercise. See, it's not just the baroreceptors that play a role in regulating blood pressure during physical activity. Our body's constantly monitoring a lot of our internal environment, right? And part of this is that when we start to increase the intensity of physical activity, there are a lot more changes in the chemical and the metabolites within our bloodstream that occur once we start to increase the intensities of contraction, as we increase the recruitment of more motor units. As motor units are working at higher intensities, we get more, as we discussed in previous lectures, we get more production of metabolites. things like lactate, adenosine, right, nitric oxide. All these things are going to start to released into the bloodstream. And not only that, our levels of CO2 and O2 are going to adjust based on intensity of exercise, right? So what we're actually seeing here in the bottom right is the chemoreflex, or sometimes referred to as the metaboreflex, right? So the change in the chemical makeup of our physiology during high intensity exercise as compared to low intensity exercise, once we start to produce more of those metabolites, right, we're going to see a blood pressure response. So again, during low intensity activity, you're not going to get as many of those metabolites. You're not going to get a huge deviation in the O2 levels and the CO2 levels. But once intensity of activity increases, there's going to be a detection of these metabolites, and that's going to send signals to the medulla to help to increase blood pressure, right? So overall, these charts show us two things: that one, the baroreceptors actually help to increase the blood pressure response during physical activity, and two, that the chemoreflex or the metaboreflex serves as a backup to regulate blood pressure during physical activity, right? And then, so here we see, even though there's a drop in blood pressure right away, once these metabolites start to accumulate, those signals are going to be sent to the medulla to help increase blood pressure in order to help the regulation of exercise, of blood pressure during exercise, right? So why does blood pressure increase during physical activity, right? Because in theory, any increase in blood pressure should be opposed or reversed by the baroreflex, right? So blood pressure goes up, the body activates the autonomic response to help bring it back down, and vice versa, right? So is the baroreflex required to allow BP to increase, right? And as we saw in the last slides, like it needs to be intact in order for blood pressure to increase. And this can be conflicting because we thought that it has a certain role to oppose changes in blood pressures, while during dynamic exercise, it seems to be allowing for this increase in blood pressure. And the reason behind that is because we're going to have an ultimate resetting of the baroreflex that's in proportion to the exercise intensity, right? So as you go from rest to light physical activity, you're going to see an increase in blood pressure. And then when you go to high intensity activity, that blood pressure is going to increase proportionally to it, right? And so this allows us to defend a higher blood pressure during exercise, right? So we're not going to get any opposition to that raise in blood pressure. So we're able to increase sympathetic nervous activity, therefore able to increase the cardiac output, and then able to increase the vasoconstriction to certain compliant regions. And then we're going to get a resting prevailing, right? So what our blood pressure was before, that's going to be perceived as hypotension, right? So we're not going to be allowed to stay at this lower blood pressure. We're going to reset to a higher blood pressure. And so what is going to happen in response to this is that we're going to increase our sympathetic nervous activity, which is what we want during exercise. We want that increase in cardiac output and increase in mean arterial pressure during physical activity. But there is a limit to how much is reset, right? And so that brings us now to here, where we're seeing the resetting of the baroreflex during physical activity. And these two graphs break it down separately. This is from Dr. Raven's work here. I will post that to our iCollege, that study there that shows the figure in the description. But here we see two separate responses. The carotid cardiac baroreflex and then the carotid vascular baroreflex. So what changes are occurring to our cardiac response in regulation of blood pressure, and what changes are occurring baroreflex-wise to our vasculature circulation? How do each of these contribute to blood pressure regulation as we increase intensity of physical activity? So first, let's just look at the basic graphs themselves. One, we see a resting baroreflex, right? Similar in each, with the operating point, this black circle here, right next to the center point. And again, we refer to that as our maximum gain or maximum sensitivity. And the similarity between these two responses, between the cardiac and the vasculature, is that this maximum gain, this maximum center point, is never going to change during, intensity of exercise. So as we go from light to moderate to heavy to max, the maximal gain will not change. However, we do see differences between these two responses as we increase our intensity activity. The first thing that we're going to notice is that, again, just a similarity for each, we do get this resetting of the Baroreflex curve, right? Where as we increase intensities of activity, our operating point does go a little bit to the left of our max gain, right? So that means our operating point is actually serving at a lower sensitivity, at a lower mean arterial pressure than our center point. And that is to help with the sympathetic nervous system response. So, but when we're looking at the differences here, we see that as far as our threshold and saturation are concerned, for the cardiac response, as we increase our intensity of activity, that operating range becomes smaller and smaller and smaller. And this operating point becomes closer and closer to that steeper portion of the curve. While the vasculature response, right, the changes in the vasculature tone during physical activity, right, there's still going to be an upward shift, but that operating range remains the same. And so what does this mean? It means that basically that as we increase the intensity of exercise, the cardiac response is going to contribute less and less to the actual regulation of mean arterial pressure. And that the changes in mean arterial pressure that are going to occur are going to come from the changes in the vasculature baroreflex, right? So in order to raise, sympathetic nervous activity and then therefore blood pressure, during dynamic exercise, as we go towards those higher limits of physical activity and those higher intensities, we're going to need to rely more on vasoconstriction to regulate blood pressure than the cardiac output response. And the reason for that is that because most of the production, most of that pressure being produced by the heart, most of that blood flow is actually going out to the skeletal muscles. So the skeletal muscles are using large quantities of that cardiac output, and therefore it's not contributing, as we increase the intensity of exercise, it's going to contribute less and less to the actual blood pressure response because that blood's going directly to vasodilated pathways of the skeletal muscle system. So therefore, we need to rely more on changes in other parts of the vasculature. We need to vasoconstrict other areas of the body in order to maintain a higher mean arterial pressure. So I'm going to end it off there for today, but the next video is going to discuss, okay, now we have a change in blood pressure response as we go from lighter to more intense physical activity. But what happens at that maximum point? Because the body basically has to decide. Again, we need to vasodilate to the skeletal muscle because we need to deliver blood, we need to deliver oxygen. But at the same time, we're concerned with our mean arterial pressure. We need to regulate that mean arterial pressure. If TPR is decreasing because of the skeletal muscle dilation, right? Where does that, that balance act, where are we going to basically be at as far as maximal exercise is concerned? So again, we'll talk about that more in the next video.